Okay, remember last time we defined the Lebesgue integral of a bounded measurable function. In particular, we said f is Lebesgue integrable if the lower and upper Lebesgue integrals are equal, where the lower Lebesgue and upper Lebesgue integrals are given by this supremum and infimum respectively. And if this is true, that these two are equal, the lower and upper Lebesgue integrals, we denote that common number by this symbol here. We just call it the Lebesgue integral of f of x dx. Okay. And I also mentioned that the upper and lower Lebesgue integrals really don't require f to be measurable. Because all we're doing here is we're looking at the set of all integrals over simple functions less than or equal to f on e. Here we're looking at the set of all integrals of simple functions bigger or equal to f on e. All these simple functions are well defined regardless of whether f is measurable or not. Okay. Right. So we also proved that if f is Riemann integrable, then f is Lebesgue integrable, and the two integrals coincide. So the Lebesgue integral generalizes the Riemann integral. And this e should be a to b. And we also proved this important theorem that bounded measurable functions are Lebesgue integrable. So you might ask the question, since you don't need measurability to define the upper and lower Lebesgue integrals, does Lebesgue integrable imply measurable? And yes, as long as we're dealing with a bounded function. So if f is bounded, e has finite measure, then the lower and upper Lebesgue integrals coincide precisely when f is measurable. And this is not the quickest thing to prove, and we don't have the tools at our disposal yet to prove it. This is theorem 7 in chapter 5 if you want to look ahead. Depending on whether we have time or not, we'll get to it. We'll prove it or not. Or as usual, in a course like this, we're slaves to time. But anyway, so let's get to something more important, but perhaps more mundane. Let's prove that the Lebesgue integral is linear in the usual sense, and that's monotone in the usual sense. All right. So yeah, we proved this for f and g. We proved this rather for simple functions, that the Lebesgue integral over simple functions is linear. Right? And that was not the quickest thing ever to prove, and neither is this, because all we have at our disposal is the upper and lower Lebesgue integral definition of the Lebesgue integral, and those involve imps and sups. So we have to equate, imps and sups essentially. So it's going to take some work. Not hard, but it's going to take some work. So what I want to do is first prove, for one, the case when beta is 0. So in particular, I'm going to prove that I can pull out constants from integrals, and then I'm going to prove that the integral of a sum is the sum of the integrals. If I do that and combine the two together, I'll get 1. Okay, so let's assume alpha is not 0. If alpha is 0, there's not a whole lot going on here. Alpha f of x is 0. So I integrate 0. 0 itself is a simple function on e. By definition, that's going to be 0. Well, f is Lebesgue integrable because it's bounded and measurable. So this exists, this integral. So it's 0 times this integral of 0. So 0 equals 0 if alpha is 0. So not a whole lot to prove. So assume alpha is not 0. All right, so let me just go back to the definition of the lower Lebesgue integral. The upper Lebesgue integral. Okay. So the definition is going to be the infimum of all these integrals here over all these simple functions. Okay, so the infimum is the greatest lower bound. I add something positive to it. It's no longer a lower bound. In particular, again, this Lebesgue integral coincides with the upper Lebesgue integral is an infimum. If I add epsilon over alpha to that infimum, it's no longer a lower bound. So there's one of these integrals that's less than, we don't care about less than or equal to is fine. But there is one of these integrals that's less than this, this here, this the infimum plus this positive number. Okay, now let's call that psi tilde. All right, so I know I can pull out constants from integrating simple functions. We proved that 2 videos ago. So I do that. And I take this alpha and distribute it throughout this inequality. Alpha is positive. So I get alpha integral f of x plus epsilon. So I'm going to use the upper Lebesgue integral definition one more time. So remember the definition is it's going to be the infimum of all these integrals here. Okay. Well, I have a nice simple function bigger or equal to alpha f. Particularly, alpha psi tilde is bigger or equal to alpha f on E. So I use the definition of the Lebesgue integral as the upper Lebesgue integral. This infimum, the infimum over all these integrals is less than or equal to any particular one of these integrals, and in particular, because alpha psi tilde is one of these simple functions, the infimum is a lower bound for all these integrals, so it's less than or equal to the integral of alpha psi tilde. But we already got that this integral is less than or equal to alpha f of x, alpha integral f of x plus epsilon. So because this is true for all epsilon, we have half of what we want to prove, at least for alpha positive. Actually, we'll see that this, just getting this inequality proves the other direction, the other inequality, fairly easily. Or rather, this being true for all alpha, not 0, gives us the other direction that we want to prove equality. Okay, this is if alpha is positive. If alpha is negative, we have to be a little more careful. So let me remind you of the lower Lebesgue integral definition for the Lebesgue integral. So this is the supremum of all these integrals. So if I add something negative to the supremum is the least upper bound. Add something negative to the supremum, it's no longer an upper bound. So in particular, the Lebesgue integral is this supremum. I add this negative number. It's negative because alpha is negative. It's no longer a upper bound for all these integrals. So particularly, pick one of these integrals that's larger than the supremum plus this negative number. Again, the supremum plus this negative number is no longer an upper bound, so I can pick an integral that's bigger than that. Again, I don't care about bigger or equal to suffices. Okay, so we do the same thing, and we're doing this because when we multiply everything out by alpha, the inequality gets switched because alpha is negative. So I multiply both sides by alpha, or rather, I take this integral here, pull out the alpha. I can do that for simple functions, positive, negative, doesn't matter what alpha is. I can always pull out constants from the integral of a simple function. And the inequality goes the other way because alpha is negative. So alpha, this integral, is less than or equal to alpha integral f of x plus epsilon. Okay, so now let's go back to the upper Lebesgue integral definition for the Lebesgue integral. Remember, the Lebesgue integral is the common number, the upper and the lower Lebesgue integral, because f is Lebesgue integrable. Okay, so the remember, it's this infimum here, the infimum of all these integrals. So I have a particularly nice simple function that is bigger or equal to alpha f on E, and that's alpha phi tilde. Because the inequalities switch, because alpha is negative. When I multiply both of these by alpha, the inequality switches. Alpha phi tilde is bigger or equal to alpha f, again, because alpha is negative. Okay. So alpha phi tilde is bigger or equal to alpha f. The infimum is the least upper bound of all these integrals. So as a lower bound, it's less than or equal to this specific integral here. Okay. Again, the Lebesgue integral coincides with the lower Lebesgue integral. Sorry, it coincides with the upper Lebesgue integral right here, just like it coincides with the lower Lebesgue integral. On the other hand, we already showed that this integral here is less than or equal to basically what we want. Again, this is true for all epsilon. So we get the inequality we want for alpha negative, and hence for all alpha. Well, we're not even worrying about alpha 0 because we already proved what we want when alpha is 0. But for both alpha positive and negative, this is going to be true. So how do we prove the other direction? Well, we do a little bit of a trick. It's an easy trick. So if alpha is not 0, then I'm going to write this integral here in this funny way, multiply and divide by alpha. And I'm going to do that because 1 over alpha is not 0, so I can pull it out. We prove that regardless of whether alpha is whether alpha is positive or negative, I can pull it out and get less than or equal to. So I do that, and the alphas cancel, so I get exactly the other half that I needed. So this half is proved for all alpha, not 0. And using it, we just proved the other direction. This integral here is less than or equal to this integral here. Okay, so again, just a little trick to write it this way to get an alpha inside the integral and then pull out this 1 over alpha. All right. So yeah, that proves it. So let's prove the additive property of the Lebesgue integral. And again, this is kind of a pain in the ass. We have to, we have to integrate, or rather, we have to play around with soups and imps and all that. So, but it's not too bad. All right, so. Right, so how do we prove this? Well, I'm going to prove half of it. I'm going to prove that this is less than or equal to the sum of the integrals. You're going to prove the other half, that the integral of the sum is bigger or equal to the sum of the integrals. Okay, so again, let's go back to the lower Lebesgue integral definition. Okay, so I'm going to apply that to f plus g. I'm going to do the same thing I did before. We subtract something positive from the supremum. Supremum is the least upper bound. Subtract something positive from the supremum. It's no longer an upper bound. So we're going to find, so yeah, we're going to use that fact that it's no longer a upper bound. Okay. So actually, sorry, I'm going to use this fact to F and G individually. Okay. So particularly pick phi 1 and phi 2, where phi 1 and phi 2 respectively are less than or equal to F and G. And these two inequalities are true. Again, I can do that because this is the supremum. Subtract epsilon over 2. It's no longer a upper bound for all these integrals. Pick one of these integrals bigger or equal to this number that's no longer an upper bound. Do the same thing for this integral here. Again, the lower Lebesgue integral is supremum of all these integrals. So subtract epsilon. I can pick an integral, pick two of them here, one for F, one for G, that are respectively bigger or equal to the supremums minus epsilon over 2, neither of which are, upper bounds. Okay. So now I'm going to go back and again use the lower Lebesgue integral definition of the Lebesgue integral, this time to F plus G. Okay. So in particular, this phi 1 plus phi 2 is a simple function. It's less than or equal to F plus G on E. And because this is the supremum of all these integrals, the integral of F plus G, well, it's bigger or equal to this particular integral here. Okay. So again, we have a nice simple function, phi 1 plus phi 2, that's less than or equal to F plus G on E. So this is an upper bound for all these integrals. So it's bigger or equal to this particular integral. But we know that the Lebesgue integral is linear for simple functions. The integral of a sum is a sum of their integrals for simple functions. So this is going to be equal to the sum of these integrals. But this integral here is bigger or equal to this integral minus epsilon over 2. This integral here is bigger or equal to the integral of G minus epsilon over 2. So add those two up. We get the integral of F plus G is bigger or equal to the integral of F plus the integral of G minus an epsilon. This is true for arbitrary epsilon. Therefore, it's true without the epsilon. So we get half of what we want. And actually, my apologies, we proved the half I said you're going to prove for homework. So the half I said we're going to prove will actually be for homework. And it's basically the same thing. You're just fiddling around with, you're going to use you're going to use the upper Lebesgue integral definition and play around with infimums a whole bunch of times. 3 times, in fact, just like we did. We played around with the definition of supremum 3 times, but it's basically the same proof. Okay, and last but not least, just like before, proving monotonicity of the integral is very easy. So, right, so the integral of f of x is less than or equal to the integral of g of x if and only if this integral here is bigger or equal to 0. Okay. And we know that integration is linear. So we need to prove that this integral here is bigger or equal to 0. So let's more generally prove that if h is bigger or equal to 0 and it's bounded measurable on E, then this integral is bigger or equal to 0. And we still have to use the definition of the Lebesgue integral, but that's easy. Particularly, it's easiest to use the upper Lebesgue integral definition. Okay. So pick some simple function, psi tilde, bigger or equal to h, which means psi tilde is bigger or equal to 0 on E. Then just check by the literal definition of a Lebesgue integral for a simple function that trivially implies that this Lebesgue integral of psi is bigger or equal to 0. Because again, if psi tilde, because if psi tilde again is bigger or equal to h, we're assuming h is bigger or equal to 0 on E, then psi tilde is bigger or equal to 0 on E. So by definition of the Lebesgue integral for simple functions, this is true. It's bigger or equal to 0. Okay, well, what does this say? This says that 0 is a lower bound for all these integrals over all these simple functions bigger or equal to h on E. Okay? But, and again, we're assuming h is bounded measurable because g minus f is bounded measurable. So it's Lebesgue integrable, so the Lebesgue integral coincides with the upper Lebesgue integral. But this is 0 is a lower bound for all these integrals. The infimum is the greatest lower bound, so the greatest lower bound is bigger or equal to this one lower bound, and so that proves linearity. Okay, so we're going to prove some important consequences in the next video of linearity.